Yeah, okay, welcome back. Yeah, today we are going to continue the derived Stephen's equation. However, today we are going to use some different method. Yeah, we normally say that minimal potential energy approach. Yeah, this principle of the minimal potential energy is only applicable to the elastic material. It is because that the potential energy, this means that when we applied some external force into the solid structure, this solid structure will be deformed. Yeah, some deformed solid structure always can store elastic energy. So actually, yeah, when solid structure deformed inelastically, so yeah, that solid structure also can store some internal energy. However, the internal energy and elastic energy is slightly different. Yeah, let's think about plastic deformation. Yeah, plastic deformation means that the energy will be disappeared. Yeah, so yeah, some solid structure can store only elastic energy, so to match energy conservation, so that this minimum potential energy approach only can be in the elastic material only. Yeah, however, yeah, in our focus in the elastic material, so that you don't need to worry about that some plastic deformation. However, this is a very basic approach to derive the stiffness equation in the finite element method. Normally, we say that the variational method, so that yeah, variational method is normally called it the calculus. Yeah, so variation means that so we are going to derive some equation as some using some variation, so that yeah, normally we are going to find out some equation, derivation of the equation equal to 0. So anyway, so that this potential energy approach is for the derived some discretized element equation. In this chapter, we are going to derive the spring element equations. Yeah, let's check the more detail. Yeah, first use this approach method. So we should define some total potential energy in the solid structure. Yeah, total potential energy is a summation of the internal strain energy U, and then the other is external forces energies omega. Yeah, strain energy is a capacity of the internal force to do work through the deformation. Means that yeah, strain energy is a stored energy in the solid structure when this solid structure will deform elastically only. And then yeah, potential energy by external force is to deform the solid structure, we must apply some internal forces, external forces. So that, for example, yeah, we have some body force due to the gravity or other kind of pressure, and then normally we can easily apply the surface traction force on the solid structure. And then in the finite element method, we are going to apply the forces and specific nodal point. Yeah, those kind of also can be external forces. So that due to those kind of external forces, solid will deform. Yeah, the deformation energy is strain energy. However, yeah, our external force, yeah, also, yeah, some solid deform. That means that we have some finite distance, so that yeah, we can apply work to the solid structure in the point of the us. So that become the potential energy of the external force. Yeah, this concept is very similar work. Yeah, let's check the more detail in the spring element. Yeah, let's think about the forces will be applied to the spring. And then the deformation and forces curve looks like this. Yeah, we are going to use a linear spring element, so that Yeah, let's think about those kind of system. Yeah, a single spring will attached on the wall, and then we applied some forces F is end of the nodal point, so that due to this forces, the spring will deform the X. Yeah, let's think about what is the external force. Yeah, we applied forces F. This solid structure will deform those kind of lengths. Yeah, this is a external force, potential energy of the by external work. And then, yeah, let's think about internal energy U. Yeah, due to the from this deformation forces relationship, yeah, we can easily determine the internal energy of the indices system. Yeah, maybe we can easily learn that this area become energy, so that yeah, half of the F and X. Yeah, we don't know actually how much spring will deform, so that I'm going to say the X in here, and then at that time forces F, so that the stored energy only this area. And then yeah, okay, and then we need total system energy pi is half of the Fx, and then external energy. So but we need more treatment. Yeah, F equal kx, so that maybe this part become the half kx square, and then this part, yeah, we don't need to changing this part. It is because that this part is external energy, so that yeah, F itself. But this part, yeah, force become can be expressed like this, the spring relationship, so that maybe we can use those kind of equation here. Yeah, okay. Yeah, let's continue detail. Yeah, actually, exact derivation looks like this. Yeah, this is a internal energy, not external energy. So that after due to the but in here they explain this is external work. Yeah, due to the external force F, so that exact work is looks like this. Yeah, from the in the previous relationship we have those kind of function, and then after the integration, this part become the half of the F max and X maxes. So but it's very simple cases in here, so you don't need to, you don't neglect this subscribe of the maxes, so that yeah, this part is external works, but this external work exactly same to the stored in the solid structure, so that this means that is a stored energy. So yeah, this become the internal strain energy part of the spring system. So that, and then from the spring relationship, so that we can changing F into the kx, so that this part become the kx square and half. And then next part, yeah, potential energy by the external force can be expressed looks like this. Yeah, but I missed this negative sign. Due to the direction or some storing energy, it is because that when we applied some external forces, the system total energy will be decreased, so that we need a minus sign in here. So that finally total equation is looks like this. Yeah, this is a total potential energy of the spring system. Yeah, this part become a stored internal energy. This part is external energy onto the solid structure. Yeah, let's deep into the spring element more detail. Yeah, in the potential energy, using the potential energy approach method, we can derive the spring element, discretized equation of the spring element. Yeah, let's think about the single spring element. Yeah, node index 1, the other node index is 2. Yeah, and we can use the displacement variable and forces variable, and then the total length equal to L and spring constant K. Actually, this total length, we don't need to those kind of information in these stages. So anyway, from the previous slide, total potential energy is equal to the kx square minus fx. Here, x, what is the x? Deformation of the solid structure. In the previous lecture, we learned about those kind of delta. Maybe delta equal to x. So that what is the deformation? U2 is a displacement of the second element. If the U2 has a finite value, the spring will be changing, increased. If U2 has a positive value. However, U1 can have some finite values. That means that total deformation must be substitution U1, so that this part become expressed looks like this. And here and then we have two external forces in the single one element, so that here fx means that this force can move to the U2, and then F1 also can be this set of first node can move to the amount of the U1 by F1x, so that we must add the two external forces separately, so that total potential energy is looks like this. This method is very simple. If you understanding the concepts of the energy. So, and then what is the next? Let's think about. Actually, we don't know that U2, U1. Actually, in here, unknown variable. Unknown variable is U1 and U2. Actually, we already know that K. Maybe the F1x is a boundary condition, and F2x also some boundary condition will already given to describe this system. So that the only remaining variable is U1 and U2. Depending on the U1 and U2, the potential energy will varies. That I means that this potential energy is a function of the U1 and U2. And also, let's think about, when we applied some external force into the solid structure, thus this solid structure will deform freely. However, let's think about how much the solid structure will deform. There are some optimization deformation. This means that, always this solid structure become tend to the minimum energy. If this solid structure very high energy value, that means that this solid structure will very unstable. To become stable, the energy must become the lowest energy level. However, if this energy has a lowest energy value, that this solid structure will want to go to this part. So that means that remaining things, changing the U1 and U2, we must find out the global minimum energy of this system. So how can we find out the minimum part? When you heard this term of the minimum, you must memorize the optimization, and then how to optimize some equation. We need some derivation, calculus. I forgot the exact spell. To obtain the minimum value of some function from the some function, so we should derivative of this total potential energies with each variable, so that I want to find out this part become minimum. Yeah, another way, yeah, derivative of the phi become 0. Yeah, however, this total potential energy is a function of the two more variables. So that means that, yeah, we need a partial difference equation. Yeah, first using the first variable, yeah, u1 and u1 plus second variable u2, the u2 become 0. That means that, yeah, we don't know that this variable. That means that this separated individual part must become 0. So that this is a result in the previous chapter. Yeah, we have some those kind of equation, u2 minus u1 square, maybe minus f1 x, not x, u1 minus f2 u2 equal to not 0, not yet. So that, yeah, how can we obtain the, yeah, we first derived by u1 and that 2 become cancel out. However, I put this value inside here, so that this part become the, yeah, we should add it. Yeah, let's again try. Yeah, cancel out, and then we can remaining this part, and then, yeah, but yeah, sorry, we don't neglect it here. Yeah, we need minus sign in here, so that minus inside in here, and u2 changing the sign, and u1 also changing sign, and then we can cancel out this one, so that the remaining equation is a k u1 minus u2 minus f1 x equal to 0. And in the second part, partial derivative by u2 also become the, looks like this, minus u1 plus u2 minus f2 x. Yeah, we obtain the two linear algebra equation. So, yeah, this is the same result compared to the direct stipulation method. Yeah, we have two unknown variables, so that we can consist of those kind of matrix form. Yeah, this u1 and u2, and also f1x, f2x. Yeah, finally we can we reached those kind of local stiffness equations. Yeah, okay. Yeah, this is a result. So that, yeah, using the potential energy approach method, we can obtain the identically same result to the direct method. So, yeah, compared to the direct stiffness method, yeah, potential energy approach is more slightly difficult or some complex. However, yeah, compared to the direct stiffness method, this potential energy approach method can be used to the other types of the equation. Yeah, so although we are going to learn about the only solid mechanics in this lecture, however, I think that you guys already learned about various physics, for example, fluid dynamics and dynamics or thermodynamics, or if you are interested in electricity, so you can also learn about those kind of some related to physics in last year. Yeah, all physics can be described by some partial difference equation, and then they have some forms like energy. So there's some, if you can changing those kind of physics into the energy formulation, yeah, you can easily derive those kind of method. So yeah, this this potential energy approach method is a general method to derive this finite equation. Yeah, actually I normally say the stiffness equations. Yeah, so yeah, please memorize this potential energy approach method. Yeah, I think that in the spring element, yeah, especially 1D cases, yeah, it's very easy to derive those kind of equation. However, yeah, when we use many element at that time, yeah, this equation will become more complex. So yeah, but yeah, this method is more convenient compared to the direct stiffness method actually. Yeah, it is because that this equation derived from some knowledge on the physics. However, yeah, in the previous direct stiffness method, yeah, we use some very actually, yeah, I think the direct stiffness method is very simple. However, I think that there are some point to confused when we derive some equation. Yeah, it is because that we already know that the exact result. So, but if you don't know that exact relationship between some internal deformation or external forces, so that it is hard to derive those kind of equation by direct stiffness method. However, those kind of potential energy approach method, yeah, if you have some equations by to describe the energy of the system, you can easily derive those kind of finite stiffness equations. Yeah, this is a summary of the chapter 2 actually. Yeah, so that in this chapter we learned about what is the stiffness matrices, and then we learned about using the spring element we derived some local or global stiffness matrix equations. So that, and also we learned about the boundary condition. Yeah, we have two boundary condition. First, homogeneous boundary condition. The second, non-homogeneous boundary condition. Yeah, so we also learned about to assemble the global stiffness matrix equation. We use a direct stiffness method. However, similarly, I also introduced the potential energy approach method to derive the global stiffness matrix equations. So that maybe the chapter 3 and chapter 4 we are going to use a direct stiffness method. However, the 2D simulation is, for example, plane stress and plane stress cases. Yeah, we need those kind of potential energy approach method or other approach method to derive the global stiffness matrix equation for the FEM. So I'm going to also introduce another approach method. However, please remember in this chapter the direct stiffness method and potential energy approach method both. Yeah, this is end of the summary of these second chapters. Yeah, I also prepared some example. Yeah, let's follow the detail. Yeah, let's consider in the previous same example. We have a two element. Yeah, index is looks like this. First node attached on the wall, and in the end of the node is a second node, and then in the middle of the node is a third node. Yeah, the element spring element constant is a K1 and K2. Yeah, in first element and second element respectively. Yeah, and also they have those kind of displacement variable U1, U3, and U2. Yeah, F1x is a F3x, F2x is a external forces vector, and then here strain energy, internal strain energy can be expressed looks like this. We have a two spring element, so that this spring will deform. This spring also will deform. That means that we have a two deformed strain energy. K1 is a delta 1 delta 1 means that deformation of the first spring element. Delta 2 is a deformation of the second element. So then, and half of each element, this becomes the internal energy. Yeah, so in the previously, yeah, deformation of the each element can be expressed by the displacement variable. At first is a u3 minus u1, delta 2 is a u2 minus u3. Yeah, so that, yeah, for the we are going to handle this equation by matrix form. So I changing the this u3 minus u1 can be looks like this, and also I changing the vector form looks like this, and then yeah, after changing, here delta 1 square, delta 1 square is the same form of the delta 1 transpose and multiplication delta 1. In the previous slide I changing this looks like this, maybe, sorry, I forgot, sorry, yeah, u1 and u3. Yeah, let's transpose this equation. Yeah, u1, u3, and then minus 1 and 1. Yeah, this part. And then, let's think about, here, 1 by 2, 2 by 1, right? Yeah, this become 1 by 1, And then also this part, 1 by 2, 2 by 1, and also 1 by 1 and 1 by 1. This result is a 1 by 1 scalar. Am I right? And then delta 2 also can be changing the multiplication transpose the delta 2 and delta 2, so that I changing this internal strainage looks like this. And then here inside part maybe the minus 1 and 1, minus 1 and 1. When you multiplied this part, this become 2 by 2 matrices, so that, and then so this part become the 1 minus 1 minus 1 1, and then and then in front of this here, we have a u1 minus u3, and behind of this equation we have a u1 minus u3 vectors, so that inside is a 1 minus 1 minus 1 and 1. However, we have a constant variable k1, so that this looks like this, and second part also same looks like this. And then to combining these two equations, we expanded this equation looks like this. These two variable become the three variable vectors, and then this part can be expressed, so that actually this part is very similar the direct stiffness approach method, so that this is some linear algebra equations. So finally we obtain those kind of two equations. This part is a u transpose, maybe global stiffness equation, and u, so that maybe total energy. Just remember that total energy of the discretized system can be expressed looks like this. And then also external forces on each nodal point. We have a 3 nodal point, and then can be expressed, can be combining this in the matrix form. To minimize this total potential energy approach method, we should use the variational approach. That means that we are going to derive this total potential energy with respect to their internal variable u1 and u2, u3. In this stage we have a 3 unknown variable. To obtain the minimum value means that derivative value always equal to 0, that each part must become 0. So that our equation looks like this. And then how can we obtain the first? Let's try only simple one equation. In here we have a u1, so that means they cancel out, and then minus u3 plus u1, and then there are no u1 value, it becomes 0, and there are no u1 only here become 0. Similarly, you can obtain the two more equations. Yeah, first equation and second equation and third equation. Yeah, we have three equation and three unknown variable, and u1, u2, u3. So that after changing those matrix form, yeah, this is a very similar the direct steepness approach method. However, in the previous slide, I also introduced the matrix form itself, so that yeah, this is a final equation. Yeah, so those kind of way you can derive the finite, actually matrix forms of the some solid structure. So and then please memorize it. Yeah, this equation has a symmetric characteristics, and then this matrix is a singular matrix. Yeah, so that to obtain the exact value, we should apply the boundary condition, maybe in here u1 equal to 0, so that we can neglect these two column and rows, and then we finally obtain reduced matrices, and then we can obtain the u2 and u3 very simply. Yeah, this is the end of the today's lecture. So if you have any simple question, please send the email or post it on eClass. So I'm going to answer you. So I think that yeah, chapter 2 is a very simple lecture. Yeah, to know that how to derive the steepness equation in the matrix, especially matrix form. Yeah, so that after the understanding those kind of method, you can apply this method into the solid truss structure and beam structure and or plane structures. So maybe last year I demonstrated until the plane stress and strain structure, but so maybe the also yeah, using the COMSOL software, we are going to learn we are compared our theoretical result and then numerical software. So please review until this chapter, and then in the next chapter, yeah, chapter 3, yeah, at that time, yeah, we are going to learn about the truss element, and then we are going to check the exact deformation and then exact reaction process. When I think that this result will be very similar in last year in the solid mechanical lecture, so that if you don't have any idea of the background in the solid mechanics, please read the solid mechanics lecture very briefly. What is the truss and what is the beam structure? So yeah, this is the end of today's lecture. So I also uploaded the next chapter 3 lecture, so that please watch the video.